I guess it's time to go. Get started. I better get out of your way here.
Okay, well, we'll try to get everybody in their seats and we'll get this program started. Professor Peter Michaelton, our department chair.
Okay, and in a moment I'll hand this back to Leo Holberg, who will introduce this evening's Hofstadter lecture. And I just wanted to make a few remarks about Bob Hofstadter and this lecture and what it represents for the physics department. It's really a very special occasion, the Hofstadter Memorial Lecture. And as somebody who knew Bob, I think he would have just loved this series of talks, and particularly this evening's talk, but Leo will introduce the speaker. So my interactions with Bob Hofstadter started when I was actually a graduate student, and I wasn't a student of Bob's, but near the end of my thesis work, I was working on a completely different experiment than what Bob was involved in, but he came to me and said, you know, you ought to try working on something completely different, and which I did, and I owed Bob, and ever since Bob had me take a left turn or right turn, I'm sure, it must have been a left turn, but I followed Bob's advice for the last, I don't know how many years, and it's really been wonderful. He turned me into a gamma ray astronomer, and there's a whole lot I can say about that, but I won't. But that whole field, one of the key contributions was Bob Hofstadter, and he got me very interested in that and was very supportive, and I'm very grateful for that. But I think a characteristic of Bob's, and you can read it, I'm not going to read this to you, but there's a history of abbreviated history of Bob's physics career, and what I think impresses me the most is how he was a superb experimentalist. He started out in one field and ended up doing some other things that were completely different. And that's a characteristic that I think we should all be envious of and admire. And I think tonight's speaker will, I think, demonstrate that in many ways. And I think the subject is something of great interest and would have caught Bob's attention. So I'll give this to Leo, and he'll introduce our speaker.
Thank you, Peter. It's a pleasure for me to have this opportunity to welcome Professor Gerald Gabrielse from Harvard University. He really is one of the world leaders in making precise measurement of what we think are the simplest things in nature. What is an electron? What is a proton? And Professor Gabrielse at Harvard has worked many years trying to understand what the structure of these simplest entities in nature is. And I think there's a strong connection with Professor Hofstadter's work, in that Professor Hofstadter's Nobel Prize was for primarily for the work he did on the structure of the proton. And many years later, Professor Gabrielse is still looking at the structure of the proton in different ways by making very, very precise measurements of electron and proton with maybe 13 digits of precision, so that you can compare that with fundamental theories. And so he's made I don't know how many world record holding experiments he has on our understanding of the fine structure of the structure of these elementary particles. I was using this fine structure word that's connected to physics, but it's really the detailed structure, electron, proton, and even more, the antimatter equivalents of those. So we will hear in a few minutes how do you make precise measurements on these little tiny devices, and Professor Gabrielse has made great advances by trapping them and probing them in very careful, precise precision measurements. He did his undergraduate work at Calvin College, and Calvin College has produced more than its fair share of world-leading scientists. It's remarkable the number of physics professors that have come out of Calvin College. He did his PhD at the University of Chicago, and then I think as a postdoc and faculty member then at University of Washington. And then he was attracted over to Harvard, and he's been at Harvard since '87. He grew up in the Midwest, and he's now sort of in a superposition between Harvard and moving his program to Northwestern University in the next year. I think you once told me you even rode your bicycle from Boston to Chicago. Is this not true? Yes? Okay, so he's headed back to Chicago.
That was a few pounds ago.
Let's see. He's received, by my count, at least 14 prizes and awards, which I won't go into in detail. Member of the National Academy of Sciences, and 2 noteworthy awards from the American Physical Society. His new center at Northwestern University, he's the founding director of the Center for Fundamental Physics at Low Energy. So please join me in welcoming Professor Gabrielse.
Well, thank you, Leo. I guess the introduction kind of calibrates me, right? Only crazy people leave Harvard University, so you have to. That should help lower your expectations for tonight. So, oh, come on in. Are there any members of the Hofstadter family in the? Well, it's good to see you. I didn't actually know your ancestor. I don't know which ancestor it was, but it's an honor to be here. And it sounds like I would have liked him if I did know him, because it sounds like he had a great taste in physics, which means he liked to do the same sorts of things I do. So, okay, I'm going to talk today about setting traps for antimatter. That doesn't sound like a completely reverent physics topic, but I was told that this was supposed to be a not completely reverent physics talk. It was supposed to be kind of a popular science sort of talk, and I'm going to try and make it that. And I do that with some fear and trembling, right? Because, of course, I'm intimidated to be at a place like Stanford where everybody's so smart. And so, you know, you naturally feel when you come here that you should impress everybody here, especially the physicists. And so I'm gonna throw a couple of slides in which are to impress the physicists, okay, just so they take me seriously. But take that in the following spirit. When I went to Harvard, what I learned it's probably different at Stanford, but if you teach a really good course at Harvard, so it's all really clear, then the students tend to say, well, jeepers, that was so clear, we didn't really need to take that class. So what I learned is that at Harvard, and again, I'm sure it's different here, what you have to do in your courses is you have to occasionally blow your students away, right? You have to just say some stuff that they can't possibly understand, and only then will they really respect you. So those of you who aren't physicists, take those slides in that spirit, okay? I'm just treating you in the same coddling way that I would treat a Harvard student. How's that? So this is what my instructions were, and I'm going to try and take them seriously. So I'm going to start right at the beginning and say, what is antimatter? Okay, and some of you know because you're old enough to watch Star Trek. Some of you are too young to have watched Star Trek. So we have to sort of bring the education together here. How does it differ from matter? Is it interesting? Why? And then I think an interesting thing in this sort of context is pure science like this. Is this actually important for the United States? And that may be of the world as well, okay? But America first, I'm trying to... All right, then I'll talk about confining antimatter, and that's where the traps come in. Though maybe you've heard about it in science fiction, right? Because in Star Trek, when the Klingons were coming, then Scotty put more antimatter in the antimatter pod and got really worried when the containment system was breaking down, right? What is all that about? What's the real science behind that? and then talk a little bit about the science that we do with antimatter. And then tomorrow I'll be giving another lecture as part of this series in the physics colloquium, and it'll be more, it will focus more on physics topics, okay? And it will be on measurements using one electron or a few electrons, okay, to test what we call the standard model of particle physics and its most precise predictions. So that will be a different story. So what I'll tell you today is a bit of a 30-year, a bit about a 30-year story, okay? 30 years ago, some friends and I went to CERN, and it was a bit of a bluff, okay? I was a postdoc with no tenure track position, and I had no budgets. The friends who went with me were either students who wanted to work with me or friends who also didn't have permanent jobs. And we persuaded CERN to give us some antiprotons and show that we could trap antiprotons. Now, I would never do that again. I'm much too old now. I would know that I couldn't ever go for a 24-hour trial period and pull off something like that. But I was young and had nothing to lose. We went there, and it actually worked. And that sort of started the story of CERN. I still remember when I went to the first guy's office at CERN, he was the guy who had built the low-energy antiproton ring. And he asked me, they were very proud of this ring, right? They called it LEAR, low energy antiproton ring. And he asked me what energy of particles I would want. And I told him, well, a little lower than yours, about 10 orders of magnitude of energy lower than yours. He decided then I was a crackpot, okay? And so he stood up and started gently escorting me towards the door. And as a particle physicist, he next asked me, what is the luminosity? Now that's the buzzword for how many particles, per second, you're going to get. How many do you need? And, in particle physics, you pride yourself on having the largest possible number for that, right? And when I said, well, in the end, I only need one particle, but I'll probably have to waste a few in order to get there, then he really did usher me out of the door, okay? And so there was kind of a clash of cultures 30 years ago. When he became a good friend once our experiments worked, I must say. He just, there's different cultures in physics and different ways that you approach things. Okay, and as the introduction mentioned, we sort of specialize in using very high precise, very delicate probes rather than very high energy methods which smash things apart. Okay, now CERN has changed completely. They have a dedicated facility. It fills rooms much bigger than this. There's hundreds of people now working on just the sorts of projects that I had suggested when I first went there. And so it's become a big enterprise, right? So this thing has changed. Now there's if you want to read the story of that, I wrote a Scientific American article about what really happened during those 24-hour periods, part of the story that you don't usually see behind the science, but I won't go into more of that now. So what is antimatter? How does it differ from matter? Is it interesting, and if so, why? And is pure antimatter science important to our country and the world, of course? Now, some of you know what antimatter is. It's what lets you go boldly where no one's gone before. Dr. Spock certainly knew what antimatter was. And as I mentioned, Scotty always got worried about the antimatter containment. And as we talk through this lecture, I'll try and help you understand, if you don't already, why the science fiction writers wrote that. How many of you have read or seen Angels and Demons? Okay, now that book is based on the antimatter science that I'm going to tell you about today. Dan Brown also wrote Angels and Demons. So I like to say, also wrote the Da Vinci Code. And I like to say that what Dan Brown did for the Roman Catholic Church in the Da Vinci Code, he did for my science in Angels and Demons, if that helps you understand, okay? Anyway, the story is that thugs go to CERN and steal the trapped antimatter, Okay, and we do this at the CERN laboratory in Geneva, Switzerland. And then they bury the trapped antimatter under the Vatican, and they threaten to blow up the cardinals as they meet to choose a new pope. So that's one way that antimatter has made it into our culture. Another way, there's the Hapgood play by Tom Stoppard, has a bearded Russian physicist who pontificates about antimatter in it. This is a more serious work, and my ancestors are Dutch, but I must say that I was once in Moscow and was mistaken for Russian until I made the mistake of speaking. And then once I made the mistake of speaking, I got switched into the tourist line where you pay a lot more money to see the shrines in Red Square. Okay. But this is another place that antimatter shows up. So the question is, how close is the science fiction to the science that we actually do? So let's do the science behind the fiction. Now, we're all made out of matter. And we don't think about this as much as I think we should. But we're all made out of electrons, protons, and neutrons. And if you look around, okay, there's a lot of variety just in this room. And yet we're all made out of the same three particles. Bernie Sanders and Donald Trump are made out of the same three particles. I mean, who could believe that that's actually true? Okay, there's the electron. The electron is, we should annihilate them. Someone's got, okay. The electron is the small particle, and remarkably, the electron, as far as we know, has no size to it. Now, that's incredible. I mean, as an experimental physicist, I just know everything has size, okay? And yet, according to our physics theories, in a real sense, we treat the electron as a particle with no size. How can that be? I would love to be the one to have the group that discovered the size of the electron, though we've not succeeded yet. About 1,836 electrons weigh about as much as a proton. A proton has size, and it has ingredients. It has 3 quarks inside. Okay, and that's another story which I won't talk to you about today. The proton is small, but it's very measurable, right? It sets the size of the nucleus, and that's the size of it is. Besides the proton, which is positively charged, there's a neutron, which has no charge. Okay, and it has about the same mass as far as we know as the proton, okay? Actually, the neutron's a little heavier, so you have about enough mass so you can take out 1 electron and 1 proton from a neutron. And actually, free neutrons do decay, though neutrons in our bodies don't decay. Isn't that great? I mean, if you think about that, if you had to worry about all your neutrons decaying, you could get a psychosis, right? But fortunately, in bound atoms, that doesn't happen. Our reality is just full of these nifty, nifty things. So anyway, matter is what we make out of matter particles, right? You know how to make a hydrogen atom. You take a proton, you put an electron in orbit. Okay, and that's the simplest atom, and then the others are more complicated versions of that, according to people like me, though some of you know better. Okay, and you can add some neutrons to the nucleus, okay, and make the nuclei more or less stable. So this is matter. Now, we're made out of matter. Everything around us is made out of matter. Essentially, everything we see in the universe is made out of matter. So, what is antimatter? Well, to the electron, proton, and the neutron, there are 3 corresponding antimatter particles. This is not science fiction. This is well established in physics beyond any reasonable doubt. Okay, and the positron is the antimatter counterpart of the electron. Now, we called it historically the positron. It could have just as well have been called the anti-electron, right? It would have kept the vocabulary simpler, but maybe it would flow a little less well. Positrons actually do occur very occasionally in our reality. They come out of unstable nuclei when they decay, and there's a source of positrons towards the center of some galaxies, including ours, okay? And we don't know exactly what makes these, but I'm sure there are astronomers in this audience who could explain it much better than I. And then there's the positron and the electron have an opposite sign of charge. okay, and the same mass. Now those are experimental statements I'm making. In the end, you have to go to reality to find out that that's true. It's not some theorist's imagination that makes it true or not. It's what we measure in reality, okay? And so far as we know, that's true. Now, the antiproton is negatively charged where the proton is positively charged. Okay, and so again, there's an opposite sign of charge and the same mass so far as we know. I mean, that's been demonstrated to about parts in 10 to the 9, parts in 10 to the 10. Okay, that the mass of these two is the same. The neutron has no charge, so it's oppositely charged to the neutron. The antineutron is oppositely charged to the neutron by a technicality, right? Because -1 times 0 is 1, right? So it all works out. Okay, and so these two fit the pattern as well. Now, as far as we know, we could make atoms out of the antimatter particles as well as the matter particles. Because of course, if you think about what holds a hydrogen atom together, there's a positive charge being attracted to a negative charge, the electron and the proton. Now, if we change the sign of both particles and make the antiproton, which is negative, and the positron, which is positive, they still attract each other, and they have the same properties so far as we know. Now, we're actually doing experiments with that. Okay, my team and several others now that have joined us are really trying to look very precisely to see if indeed that's true. Okay, now if you can make atoms, then the question is, we take matter particles, we make matter molecules, matter cells, matter people. Why not a matter universe? Okay, well, we have a matter universe. Let's do it with antimatter. Antimatter particles, antimatter molecules, antimatter cells. Why not an antimatter people and an antimatter universe? That's actually one of the deep questions of physics, I think. That it's kind of surprising that in 2017 we still really don't have an answer to that. Okay, we currently don't know any reason why people and a universe could not be made out of antimatter rather than matter. So that brings up the question: why is it that we have a universe made out of matter? More about that in a moment. Now, how would antimatter people differ from matter people? Okay, well, we can take Gabrielse, who's made out of matter. Okay, and let's compare him to the anti-Gabrielse, okay, made out of antimatter. You religious types, that's not supposed to suggest an antichrist. This is a scientific kind of lecture. Now, would he be smarter, more handsome, less massive? Well, as far as we know, the bad news is that modern physics predicts that Gabrielse and anti-Gabrielse would have exactly the same properties. Well, exactly is a little strong. There is a way to tell matter from antimatter, but it's really, you have to build really a whole big accelerator like CERN in order to do that, okay? Because it's a very subtle difference that you have to exploit in order to tell the difference. So as far as we know, we could have people and the whole universe, in fact, made out of antimatter. Now, the big mystery is, why are people and the universe made out of matter and not antimatter, right? I mean, in science, usually if there's some question like that, that's just staring you right smack in the face, there has to be an answer that will stare you right smack in the face, okay? And I believe there is one, but we just haven't found it yet, okay? And so a lot of what we're trying to do is to try and learn enough about what we call the basic symmetries of our basic description of physics to see if indeed we can get some hints about this. I'll come back to another related mystery in just a moment. Now, what difference will it make if we solve this mystery? Okay, I'm often asked this in popular science talks, and does it make enough difference that the United States should support such pure science? And I think often in physics we don't take on this topic, though I think that we should. Okay, and the first answer is that if whatever solutions to a mystery like this we find change our basic paradigm, our basic view of physics, okay, then big consequences can come out. For example, before the discovery of quantum mechanics, scientists were very satisfied, for the most part, with the classical description. In fact, people made bold statements about how physics was sort of done. Okay, now we have, my cell phone has a zillion transistors in it, right? And quantum mechanics is a really important thing, okay? And we navigate with GPSs. None of that sort of stuff was foreseen. So that's one answer. Another answer is that scientists tend to invent things. And some of us don't worry much about applications. We do pure science, okay? But even then, we scientists discover and invent things. I can just give some examples here. The first two came from my building at Harvard. Atomic clocks were invented by, well, at least the hydrogen maser was invented by Norman Ramsey and Dan Kleppner. I was privileged to take Norman Ramsey's slot at Harvard when he retired. They never imagined that there would be a global positioning system that would make use of that. In fact, I was driving my Prius, my first Prius one day, and Norman was in the back seat and Dan was sitting next to me, okay? And I said, have you ever seen a GPS? And neither of them had, okay? And I had bought one because I had told my wife that as a friend of these pioneers, I had to buy one. It was my duty to buy one of the first GPSs, right? I mean, geeks make their arguments, right? And my English major wife rolled her eyes and I got my GPS. So I pulled it out and I got to show the inventors of the hydrogen maser that made it possible how a GPS worked. Now, they weren't impressed with the relativistic corrections, general and special relativity, and all that stuff. What they were impressed with was Gwynnie. Gwynnie is the lady who lives inside of my GPS and talks to us and gives directions. So we spent the rest of the trip talking about what algorithm Gwynnie was using to make the directions. So, okay, nuclear magnetic resonance. One of the inventors was here at Stanford, of course. Also, Ed Purcell at Harvard. Ed was one of the smartest people I've ever met. And when he was asked once, what is the use of nuclear magnetic resonance? He said, well, it's an esoteric sort of thing. There's really no applications for it. Even someone as smart as Ed didn't realize that every hospital in the world would be trying to buy as many MRI instruments as possible, okay, to image inside of a body without, giving an X-ray dose and so on. The transistor, we could go on at Bell. The laser, make a better light source. Now it's CD players, communications, grocery store checkout. The internet, they're very fond of saying at CERN that they invented it. That's partly true. In my own case, we once found out that the magnetic fields were changing at Harvard badly because the subway was going down the street. And so we were desperate and we invented a kind of solenoid, a kind of coil that made a magnetic field. And this solenoid would just cancel out the fluctuations in the magnetic field. And now that's incorporated into most MRI imaging machines. So these things kind of come. Now, it's kind of hard to sell these things. You don't want to write in your grant application, you should support my research because I might invent something that I didn't anticipate. That doesn't work very well with reviewers. But as a community, okay, that's an important thing. Okay, confining antimatter. The question here is, Scotty did it, can we? Okay, and well, let's talk about this and the challenge of the confinement, okay? Well, I have to describe annihilation, which some of you know about, but here's a simple example. If we take an electron and we take its antimatter counterpart, the anti-electron that we call the positron, and we let those two collide, and suppose we do it inside of some big bucket or something that's sort of reasonably thick, then what's going to happen is both the electron and the positron completely disappear. We say they annihilate each other. And what we're left with is a little bit of heat in the bucket. Actually, there's some photons that come out which get absorbed by the bucket. But, I mean, basically, the energy is released as heat into the bucket. Okay? And the famous formula that all of you know, and probably some of you, many of you probably even know what it means, but in our culture everybody knows this, but on balance, I'll bet you even our president doesn't know what it means, okay? E equals mc squared, that's to describe this very situation. E is the energy released if you take the mass, okay, and multiply it by the speed of light squared. Now, why the speed of light should be the thing that connects, mass and energy is an interesting question which we won't get into. But basically, you can produce quite a lot of energy, okay? So, but the important point for this lecture is when matter and antimatter come together, they annihilate, they disappear. Now, that leads to the second cosmic mystery that I want to refer to. Why do we have not only a universe made out of matter, but why do we have any universe at all? Okay, because according to our current understandings of how the universe came about scientifically, there was a big bang, a big explosion. According to our standard description called the Standard Model of Particle Physics, there should have been essentially equal amounts of matter and antimatter created. There's a symmetry there between matter and antimatter, okay? And now as right away, the matter wouldn't have run into the antimatter so easily because it was at such high energy, right, that there wasn't much interaction time. But as the universe cooled down, the matter and the antimatter particles would run into each other, okay? They would annihilate, and if you had equal amounts to start, you'd have nothing left, okay? And believe it or not, we don't understand the answer to that question, okay? And yeah, so we have what we call a standard explanation. Now this is for those who are physicists here. It's attributed to Sakurai. If we have a violation of CP symmetry, we have violation of baryon number. This we know, but this we see, but there's not nearly enough of it to account for a universe. Violation of baryon number, which we think could happen, but we've never observed. Thermodynamic equilibrium, which we don't like, even in a Big Bang. Okay, those three things together would explain how our universe could exist. But none of the elements, you know, by themselves work. So it's a big mystery. There's an alternative, which I won't go into here. So now in physics, though, you know, this is considered now a small problem. You know, why the universe exists is a small problem because we have a bigger problem. We don't understand dark energy recently discovered within 120 orders of magnitude, right? So if you're a theoretical physicist, you got to first solve the 120 orders of magnitude before you deal with the small things, like why does the universe exist? The point I'm trying to make here, though, is that even though, you know, at the turn of last century, people thought that physics was about done. Right now, we don't know most of what the matter is in the matter in the universe. We don't know what most of the energy is, and we don't know why the universe exists at all, and we don't know why it's made out of matter rather than antimatter. Aside from that, we understand everything, of course. Okay, so the good news for the young people is there's still plenty of things to do, right? You know, and you'll outlive all of us trying to solve some of these problems. Okay, now, why compare antimatter and matter? Okay, well, if you're going to do a precise measurement, and I'm known, as you heard in the introductions, for doing precise measurements, one of the hardest things sometimes is to decide what is a good precise measurement to do. Okay, the fact that it's precise doesn't make it interesting, right? In fact, if anything, if you were smart, you would figure out how to do a not very precise measurement to really settle whatever issue you're interested in, okay? And so some of us who aren't too smart end up doing these incredibly precise measurements. I mean, the distance between my nose and your nose, we could measure very precisely. It wouldn't make it interesting, okay? And so if we're with matter and antimatter, what are the interesting things to do? Well, these are the big questions. And I guess what we know is that in our standard description of physics, these things we called symmetry, for example, the way matter and antimatter should behave much the same way, this is called CPT symmetry. Okay, those are the buzzwords. I won't describe that in any more detail right now, but you know, there's either something wrong with that or one of the other symmetries we think we understand because we can't answer some of these very basic questions. Okay? Now, that's a big surprise given that tomorrow I'll show how the standard description of physics can also predict things accurately to 12 significant figures. Okay? I'll talk about how we test the most precise prediction we have of any quantity we can measure. So we went and measured it. And by George, our standard description was right. Okay, and against the backdrop that we know it's wrong. I mean, that's the situation that we're in. Okay, So let's talk about annihilation of big objects just for fun. What happens when antimatter and the matter Gabrielse meet? Well, if anti-Gabrielse is made out of antimatter and Gabrielse is made out of matter and they're about to shake hands, what's going to happen? Now, I don't want anybody to complain about ignition methods and stuff like that and getting it all to happen at once. This is just a simple argument. Okay, but let's estimate using E equals mc squared how much energy would be released. Okay, so 100 kilogram anti-Gabrielse, 100 kilogram Gabrielse. I didn't want to say my weight, and this disguises it, okay? And the energy released is equal to the mass that disappears times c squared, so 200 kilograms worth of energy. But let's put it in terms that people with different personalities can understand. For those of you who are thrifty, it's this many kilowatt hours, right? That's the one place our country is smart enough to use the metric system, right? Is in kilowatt hours on our electric bills. That's a lot of kilowatt hours, okay? My house takes about it uses about a kilowatt during the day and less at night, so it's a few kilowatt hours per day. It's the yearly output, this number, of 500 nuclear power plants. Okay, that sort of puts it in perspective. And for those of you who like to blow up things, okay, it's the energy from 4,200 megatons of TNT. Okay, so it's almost enough to make you, give up your body for science, right? If think of all the good you could do, at least in the peaceful applications, except there's a bit of a problem making an anti-Gabrielse. Now, why do science fiction writers find this so attractive? Well, all of the mass turns into energy. Okay, in fact, you get twice as much energy as the mass of the fuel that you put in, but that's really a technicality. It's because you use up some of the fuel tank, right? You have to have an antiproton annihilate with a proton which is in the fuel tank, so you're actually getting, so it's really all the fuel turns into energy. That's a great thing. If you look at an efficiency number, the energy released per the mass of fuel used, and then I multiplied by a c squared here to use Einstein's formula, annihilation is 200% efficient. It's actually 100%. I just explained why I said 200. Nuclear fission and fusion, okay, they're about 0.1% efficient. Chemical fuel is way down there, so naturally that's the one we all use, right? Because that's the least efficient, and we can make the most possible pollutants that way. Okay, so annihilation has about 1,000 times more bang for the gram compared to nuclear fuel. Okay, so that's why science fiction writers are fascinated, right? Because if you want to go to a distant star, you don't want to burn gasoline in your rocket, right? Because you got to drag along a lot of gas stations. Okay, you don't even want to do nuclear fuel because you still have to take a lot of nuclear fuel along. So if you have a shot of returning and bragging to your grandchildren, so the argument goes, then you'd better at least use the most efficient thing. Now, the question is, how much antimatter can we make? So in order to do that, I'm going to tell you how antimatter is made at CERN. You take a very fast proton, okay, any one of the protons inside my body or your body will do, and you smash it into some sort of target, which has protons in it. When they smash together, the quarks get very confused about who their partners are. Okay, it's like a modern marriage, I think. The partners don't always know where, okay. But you create a lot of extra partners, as many as you have energy for, okay, and out of the debris come some antimatter particles. Okay? Now, the problem with this process is you can release about 10 times less energy from complete and efficient use of an antiproton than it takes to make it. Right, so that's a really terrible energy source, right? I mean, it would, petroleum would be a really terrible energy source if nature hadn't been kind enough to take millions of years and prepare it for us and invite us to waste it, okay? But okay, this would be a really terrible energy source, and you have to have something the size of CERN, some big accelerator. This is a medium-sized international airport, and the CERN laboratory is going under Switzerland here in France here, okay, you need these big facilities to deal with it. But this is how it's made at CERN, and underneath the ground, okay, and there's beautiful surroundings at CERN, beautiful mountains, and then the ugliest buildings you have ever seen, right? They're made out of piling concrete blocks on top of each other, okay? Very Swiss utilitarian architecture there. But anyway, underground, mostly underground, there's all these different rings where there are particles going round and round, nursed, from these collisions. There's various particles. There's positrons, there's electrons, there's protons, there's heavy ions, there's antiprotons. They all go in these different rings, okay? And when they make all the matter they can make, there's not enough antimatter made in the history of the universe, okay, to even weigh on a scale. Okay, that's an important thing. More about that in a moment. So, is antimatter an energy source for the future? Well, certainly not. It takes too much energy to make it. Can you make antimatter weapons? Okay, now, it used to drive me nuts when I was a young physicist. We got a lot of press when we trapped antimatter, right? It was in newspapers, TV, everything, okay? And then, the reporters would do their story, and the end of the story has no morality whatsoever. The last line or two, you can say anything you jolly well please. And they would, after a perfectly reasonable story, they would say, but nobody knows what sort of implications this has for weapons in the future. That kind of line. And it used to drive me nuts, okay? I've changed my tune on that, but I'll explain that later. Antimatter rockets, maybe you could do antimatter rockets someday, because you only have one rocket or something, but it would take, right now we're nowhere close being able to make enough energy. In fact, the problem of this Angels and Demons book, okay, and the movie too, okay, is there was one missing detail. If you took all the antiprotons that have ever been made in the history of the universe and you annihilated them all together, there wouldn't be enough energy released to boil a cup of tea. Now, you see, the moral of the story is clear. The cardinals should study more science, right? And then they wouldn't have worried about this, and Dan Brown wouldn't have gotten rich on this book. Maybe I would have gotten rich instead, but okay. All right. So, now how do we contain and store charged antimatter? If it's going to annihilate, here's where the traps come in. Okay? If we want to set a trap for antimatter, we can't put it in a beaker, that's for sure, because the beaker's made out of matter. We put the antimatter particle in, it annihilates. There's a bit of a problem. So we need to build a bottle without walls. Okay? I'm going to skip this, I think. And here's the basic idea. Okay? I have to teach you two pieces of physics if you don't know it already. One is that charges near a magnet go in circles. Okay, that's one piece of truth. The second piece of truth you probably already know, and that's, oops, I got it wrong. Like charges repel. Okay? Well, that's embarrassing. Okay, well, that's been extrapolated to marriages and all sorts of things nowadays, okay? Oh, all right, I'm just trying to see if you're awake. Okay, anyway, so basically if you take a charged antimatter particle and you put it near a magnet, the arrow is the direction the compass would point, the direction of the magnetic field, we say. The particle will go in a circle. Now, it can go up or down, right? And there's nothing that keeps it in one place. And so what we do is we put negative charges above and below, and the antiproton is repelled by by those negative charges, because it has a negative charge. That's a trap, okay? So we use batteries, okay, and magnets to make a container that has no walls. That is to say, the particle doesn't ever encounter any matter at all. And so we've held in traps like this, we've held antiprotons, okay, for months at a time, okay, and just held them. Now you have to have a nearly perfect vacuum, okay, and that's another story that I won't have time to talk about. Okay, so basically here's the way we trap the antiprotons. They're going to come in here from the left. They're going to be going along the direction of a magnetic field, and then we're going to put negative charges here, but we aren't going to put the negative charges here first. So the antiprotons will crash through this matter. You say, oh, but they'll annihilate. Well, it turns out if you make the matter thin enough, you can pick the right thickness that the particles can get through before there's an appreciable probability of annihilating, okay? And if it's too thick, that won't happen, of course. So they slow down, in fact, in that material, they turn around, and before they get to the end, then we put negative charges on here so they're stuck. Okay, and then for those of you who know about potential wells, this is the same picture in terms of potential wells. For those who don't know about potential wells, you just imagine a sink, right? If I have a sink and I roll a ball into it, and then I flop the wall up, after it's gone in, right? That's a potential well picture of the same thing, at least an analog. So here's what happens. The particles come in, okay? We slam the door shut, and then they oscillate back and forth. Okay, and then what we do is we say, well, let's slow these particles down. Well, it's really easy to slow things down with friction for macroscopic things. It turns out it's really hard to slow things down, okay, if they're microscopic. And especially for elementary particles like these, it's very difficult. So what we do is the following. Well, I don't have a picture here. What we do is we put a cloud of electrons in there. Electrons are the only matter species that when antiprotons hit them won't annihilate. There's no mechanism for them to annihilate, it turns out. Okay? So we put them through the electrons and we slow them down. Now, it's kind of like, since they're 2,000 times lighter, it's kind of like slowing your car, instead of with brakes, by driving it through ping pong balls, right? A room full of ping pong balls. That's not a great way to slow your car down, but if it's the only choice, then it makes it easier to choose it, right? And this is the only matter species that can do it, and so that's why we do it that way. Okay, now there's various ways to detect antimatter. The way I'll talk about here is we listen to the radio, okay? So if we take an antimatter particle and we make it oscillate in a circle, okay, then and we put an antenna nearby and attach an FM radio to it. Now, some of you younger people, this is the old-fashioned kind with a knob that you haven't seen. This was before buttons and displays and stuff, okay? But it's the same thing. So you tune the knob. And if you tune the knob, you get this really boring radio station. It really has a really narrow signal, no modulation on it, so there's no music, no anything. But it tells you the frequency. You can measure how fast it's going around in a magnetic field. Now you can put a proton in that same magnetic field. It oscillates at the same rate. At least that's what our physics theories tell us, except in the opposite direction. You can listen to the same radio and you can compare back and forth to see whether they're the same or different. So that's the way we do those sorts of measurements. Okay, now we've done a lot of different measurements. Here's just a summary of what we've done. Okay, we compared the proton. Well, here's at Berkeley when it was discovered. It was compared to the antiproton. Okay, at a precision of parts in 10 to the 4, which is a fairly high precision. We improved things by almost a factor of 1,000,000, and then our result was confirmed a couple of years ago after a 16-year lag. Okay, and basically the idea is we failed to find any difference between the proton and the antiproton, so our standard description so far is right. Now, we think we can measure it much more precisely still, and so we're going to try and do that. We've compared the gravity of antimatter and matter using something called the gravitational redshift. I think for lack of time, I'm not going to explain that right now, other than to say that some of you have heard of, if you take a clock and you raise it up, okay, above the Earth, the gravitational force on it changes. It goes at a different rate. This is well demonstrated. Okay, it's been done with atomic clocks on airplanes, for example, but other contexts as well. Well, that's one way to change the gravitational force. If you take your clock and change it from matter to antimatter, that's another way if gravity is different for matter and antimatter. So we made a matter clock, a proton going round and round, and an antimatter clock, an antiproton going round and round. And by comparing the two, we could set a limit. And gravity is about the same to at least a part per million by this argument. Okay, we've measured the magnet inside of an electron, inside of an antiproton. We did this a couple of years ago to only 4 parts per billion yet. We made a 680-fold improvement in the measurement, which we were quite proud of. But what's even more exciting, we think we can go another factor of 1,000 or 10,000 times more precise and compare the magnet in an antiproton to a proton. Again, the spirit is the same. We're looking to see if nature is going to reveal some secret to us about where these symmetries are violated. Okay, now tomorrow I'll tell you about an electron experiment which does a similar sort of thing but uses a lot of quantum mechanics and other stuff to do this about 10 million times more precisely. Okay, I don't know if we can ever do the proton and antiproton measurement as accurately as we've done the electron, but we can do it a lot more accurately than we've done now. Okay, so now we also can make traps for antimatter atoms, and so I'm going to kind of conclude with a discussion of that. Now, first let me give you the reason. If you look in the hydrogen atom, all of you know from high school chemistry that atoms have energy levels, and when the electron pops between one energy level and the other and then comes down, there's photons that come in and come out and that sort of stuff. Okay, and it turns out that if you pop in the hydrogen atom, if you pop the electron up to this 2s state, it lives for about 1/7 of a second, and you can measure this transition exceedingly precisely. Here's the precision that's been done with hydrogen over the years, and there's a ridiculous precision that's been achieved. Okay? What we'd like to do is measure this same transition with antihydrogen and compare it to the hydrogen atom. Again, you see the thing. We're going to take an atom made completely out of matter and compare it to an atom made completely out of antimatter to see if indeed they're the same. Okay, and if they're not, that of course would be a really wonderful thing. Now, we proposed to do this many years ago. At the time, it was I almost didn't publish the idea to do this because at the time people were thinking about doing these only in beams, and so doing it in a trap people thought was kind of weird. It turns out now there's, like I said, a couple hundred people working on it, and the way you can't trap an atom the same way as you trap the particles I've told you about. Okay, right? The charged particles were repelled by like charges, right? And they orbited in the magnetic field. Well, a neutral particle like a hydrogen atom or antihydrogen atom does neither of those two things. Okay, so you can't make a trap that way. You have to do it differently. Now, this isn't how we do it, but I just couldn't resist showing you the movie here. Okay, this is a frog that's in there. And, something went wrong with my graphics here. Anyway, there's a frog suspended in a magnet, and I claim the frog is having fun. I didn't do this experiment, so don't send me your animal hate mail, okay? I claim that the frog may be having a lot of trouble because it's the most free experience he's ever had. He's weightless, after all, so to speak. But you can suspend a frog that way. That's not how we do it with antimatter, but it's a related idea. Okay, and so let me show you basically the idea here. If you put, this is known in atomic physics, if you take 4 current bars, and these long bars here, are meant to be a current going this way, 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 and then you put currents on the ends, it turns out you can make the magnetic field, the size, how much deflection your compass would do, you can make it minimum at the center of this thing. Okay, and it turns out that an atom in the right state will sit in the minimum of a magnetic field. So if we take hydrogen or antihydrogen, we can make a trap without walls, right? Because it's magnets that we're using to suspend this, and we can hold it there. And you can add as many bars as you like, okay, subject to having an even number or something like that. And what we do is we take the traps that we trap protons in, okay, and the traps that we trap positrons in, we move the antiprotons and positrons together, and we put it into one of these Yaffe trap sorts of things, and that captures the antihydrogen atoms, again in a trap without walls. Okay, and that works. Okay, there's 2 collaborations that have done it, our collaboration and another. We managed to get about 5 atoms per trial in there, not very many atoms. Okay, and so we're working hard to get more atoms in the trap right now. But again, the important thing is to have a signal that you can start to optimize. So these sort of traps, this is a different kind of trap, it's technologically challenging. In our new trap, it takes nearly 1,000 amps of current. Okay, that's a fair amount. Okay, it means that there's enough energy stored in this coil that it will destroy the coil. Okay, if anything goes wrong, okay? We need to do this at superconducting wires, only 4 degrees above absolute zero. I mentioned this. We're only millimeters away from electrodes which are at 1 Kelvin, 1 degree above absolute zero. We have to switch it on in just seconds, and we want to switch it off in tens of milliseconds. So there's a lot of technological challenges in that for those of you who know about this. Here's how we did it, is we took the superconducting wire and we buried it in the backside of printed circuit boards, G10, this sort of material that some of you physicists know about. Here's the wires impregnated. And you can see here's various coils and things with trap electrodes inside. And we can make these beautiful pictures. What these are is sort of sync pictures, potential energy pictures. And this shows you the deepest part of our trap is here. And then it gets shallower as you go out. And I don't have time to talk about the configuration right now. But laser-cooled antihydrogen would occupy these 2.5 millikelvin contours here in this octuple trap, and a similar contour in this quadruple trap. The quadruple trap has only 4 current bars, and the octuple current trap has 8. And I don't really have time to talk more about the reasons for that. There's a lot of technology that goes on in these sorts of experiments, and I would love to talk to you about it, but let me just say that there's a lot of machining. When you do this sort of work, you spend a lot of your time being an engineer, okay? Because unless an apparatus like this is engineered really well, it won't work, okay? And so here's where I made probably the biggest blunder of my scientific career. I don't know if this is a good time to mention this, but we had this coil shown here. It's all potted together in epoxy fiberglass. Costs $500,000 to replace, okay? And I said, well, we can get a little more trap depth, a little more deep, make this well a little deeper if we don't use metal to surround this for a vacuum container, but we glue together an epoxy fiberglass vacuum system. And we built 3 full-size prototypes, all of which worked. Then you guessed it, we built the real thing and it didn't work. Okay, and it turned out that with the glue joints on this epoxy, we could never keep this thing inside at an equal enough temperature to avoid straining the joints. And this set us back by a couple of years. One of my worst experiences, I think, in my professional life. And it's especially hard if an old guy like me makes a bad decision and then the young people suffer for it. But we ended up then making it out of titanium, okay, and E-beam welded, you know, 6-7 inches deep inside it. It was really a tour de force, I think. Here's just some pictures of putting it together. In the end, though, we could turn on our second generation Yaffe trap in somewhere between seconds and tens of seconds, okay, which is a good thing because we otherwise would lose the charged particles in the gradient fields and because they were changing. We also could remove the current in much less than the 10 minutes of our first trap. In fact, here we can remove it in just 10 milliseconds or so, okay, and so there's been a lot of progress here. Some interesting things happen that might interest the physicists. When you turn off a big current like this, and you turn it off in 10 milliseconds, there's a big inductive kickback, okay? There's a couple of kilovolts, right? So you have to be careful you don't get killed when you do this. And so that's one thing. The other thing is we have these copper electrodes inside that we use for the trap. And even though we put splits in them, in order to keep eddy currents from flowing. There still can be sideways eddy currents. And it turns out that when we dump the trap, we see eddy current heating on temperature sensors, okay, connected to these electrodes. So it's really hard to keep the coupling down. Lots of interesting stuff. I'm not going to tell you about all the lasers we're developing right now, but we're at the situation, at the stage where we have trapped antihydrogen atoms. What we would like to do is laser cool these, okay, even though the laser cooling is not such good laser cooling because the hydrogen atom is not nearly as massive as it should be, so to speak, and the photon has way too much energy, so the cooling limit is only 2.5 millikelvin, okay, but we made 120 nanometers, 121 nanometers of light at CERN, and that's a new record, I believe, for that sort of thing. Okay, I'm going to conclude here and just say that what I've tried to give you today is some sort of feel for why we do these sorts of experiments and what some of the challenges are, what we spend some of our time doing. Now, you know, I kind of summarized 30 years of work, so I might have skipped a few details, okay? But you know, when you try and, the secret to good teaching is to teach your students honestly, okay? And I've tried to do that, okay? The big questions that we're trying to focus on is, why is the universe made of matter rather than antimatter? We don't know. Why did our matter universe survive annihilation as the universe cooled after the Big Bang? We set traps for antimatter and matter to look for hints of these sort of answers. And then I want to remind you that pure science is the needed fuel for a technological society. So pay your taxes, whatever the Republicans tell you to do this year. So, all right. So.
Time for a few questions.
Is there a path or a roadmap for higher Z antimatter?
Yeah, it's step aside and let something for the younger generation to do. It's hard. I think it could be done, and I think in principle you could sort of redo all of chemistry, I suppose, though it's really hard given the containment problems with antimatter. I don't really see the reason, okay, but that's a matter of taste. For me, if once we look at the simplest particles and the simplest atoms, and we fail to find or do find a symmetry violation compared to what we expect now, that will be enough for me. You can make machines that have deuterons in them, okay? You can make anti-deuterons as well. They also come out of the degree, but in less copious numbers, so you have to have a source with more luminosity. You could do all this stuff. People sometimes talk about it. I'm personally not so interested in it right now, but you know, some young person will quote me on this someday and say that what a dumb advice I gave by saying don't bother to do that, and they'll explain why. But no real serious path, I think, right now is available. Mm-hmm. You'll have to speak up. Yeah.
You mentioned that you're working on doing laser spectroscopy and anti-hydrogen.
Yeah. Yeah.
Is there any hope to obtain the same level of accuracy?
Well, hope. Yeah, hope is easy. Of course there's hope. Realistic expectation? Well, here's the challenge. When Ted does an experiment, right, he has a hydrogen bottle sitting there, right, and he opens the spigot, okay, and almost without doing anything, a little bit of microwave ionization, he makes a density of 10 to the 12 per cubic centimeter atoms coming out. You know, we're going to be working with a few, okay? That's a big, that flux change, that number is a big hit. Now, having said that, when we started with low energy antiproton physics, then it was at that time, doing an experiment with just one trapped antiproton also seemed fanciful, right? And it took us a decade or so in order to develop all the methods and so forth to do it. In the end, we did just as we hoped, namely we did our very best very best measurement with one antiproton and one H minus atom together in the trap for technical reasons that I didn't take time to talk about. I think that over time, we should be able to do spectroscopy with one or not too many atoms, okay? But we're a long way away from that. The shelving scheme, which you probably know about given the question you asked, is one that should work, okay, with antihydrogen atoms, because you have the 1s2s transition, and then you have a cycling transition, the 1s2p. And so I think there's some hope, but I think, you know, in the end, I hope that we will end up doing spectroscopy with just one atom at a time, but I can't prove to you that that's feasible at this point, okay? And I'll say this, that Ted Hinch has voted with his feet. He's not even trying to do spectroscopy with only one atom, even though I've tried to persuade him many times to do that. He thinks it's much easier, and he's right, to do it with a whole bottle full, so to speak. That's what he prefers.
But it would be interesting at some point also to determine the size of an antihydrogen.
Yeah, well, the size, you know, there's a whole nother story about that, but yeah, yeah, sure.
Another question?
You described some of these very precise measurements that
Yeah.
seem to confirm certain aspects of the standard model, yet you have these big fundamental questions up here.
Yeah.
So what are the chances that physics, there's some fundamental lack of understanding about something, like there was back in the days of the Michelson-Morley experiment that took an Einstein to explain?
I don't know the answer to that question. Okay, I think it's a valid question to think about. I mean, there's clearly something wrong, right? I mean, there's clearly a lot of stuff we don't understand, and it's not like we don't understand it a little bit. We don't understand it a lot. Okay, so from that I jumped to the conclusion that there's something fundamental we're missing. Now, a lot of physicists like to describe it as we just have to modify the standard model a little bit. Well, maybe that's true. That's as much an article of faith as anything else. We just don't know at this point. So I think it's a very intriguing state of affairs, and I don't know how to answer your question. And I'm not trying to dodge it. I just don't know how to answer it. Yeah.
One more. Well, we got a couple. Go ahead.
Can you measure the gravitational force on the antihydrogen?
Yeah, I think that it certainly should be easier than with antiprotons, okay, but it's not so easy. The most speculative paper I ever wrote about was called Antihydrogen Gravity, Can We Measure It, or something like that. And it's really hard. I mean, the whole Earth pulling on an antihydrogen atom is like taking one elementary charge 10 centimeters away and pulling on it. So you've got to clear out these electromagnetic forces, right? The electromagnetic force that holds atoms together is so much bigger. So you've got to really be careful about that. There are experiments we actually measured with the antiproton to a part per million already, a part in 10 to the 6, and showed that the gravity was the same. There's a couple of experiments at CERN right now, part of the same working in the same area, which are aimed at doing gravitational experiments. I don't think they're going to get a part per million accuracy even, because I think they're much harder experiments than that. But you know, you have to be careful about saying what you can and can't do, because you know, as you get into things, sometimes you invent new methods. But the answer is yes, you can. Yes, we have. Can you do it at an interesting level of precision, which might be parts in 10 to the 10 or parts in 10 to the 12? I have no idea how to do that right now, and I don't know of anyone who does.
We'll take one more question. This one here.
Since matter and antimatter act so similarly, you look up at the...
Can you speak just a little louder? I'm hearing some people.
When you look up at galaxies that are so
Yeah.
far away that they'll never interact, how do you know that some of them aren't made out of antimatter?
Yeah, that's a good question. I mean, there have been experiments to look for antimatter coming from space. I think that the basic argument is that there are so many galaxies and so forth that if there were matter and antimatter galaxies, we would be seeing evidence of annihilation happening, and we don't. Okay, the only antimatter evidence we see, well, two things. I think I mentioned that we see positron sources near the center of some galaxies. Okay, there are also some antiprotons made, but it's when cosmic rays come in and hit the nitrogen and oxygen in our atmosphere, and they'll make, but that's a rate that you can estimate and measure and, you know, go deeper in the atmosphere and see what's going on. So I think we believe that there would be evidence of that. Of course, you can't ever say no, but the limit you set is well below the limit, you know, that would explain the imbalance of matter and antimatter in the universe.
Besides, you know, the fact that there aren't any annihilations, is there anything from just looking at a far-off object you could tell if it was matter or antimatter?
No, not that I know of. Okay, like I said, there's only one way to tell. You have to do a CP violation experiment, which takes a very large accelerator. Okay, and that's the only way I know of to tell the difference between matter and antimatter. Okay, and you know, that we can't do from a distance.
Okay, so why don't we thank Professor Gabrielse for a nice talk.